The popular image of the early Earth is a sterile, fiery ball of magma, a planetary-scale version of Dante's Inferno. But the geochemical record tells a different story. Almost immediately after its formation, the planet began to organize. Look closely at this terrain. These are among the oldest surviving rock formations on Earth. Chemical signatures locked inside ancient crystals from similar early crust tell us that the surface had cooled enough to support liquid water oceans roughly 4.4 billion years ago, practically right after the planet formed. In those early oceans, microscopic biological engines came online. Microbes known as cyanobacteria were using sunlight to photosynthesize, pumping out oxygen gas as a waste product by at least 3.5 billion years ago. Biology began producing oxygen here as early as 3.5 billion years ago. Yet the gas didn't actually flood the atmosphere until 2.4 billion years ago. That's a billion-year gap in the geological record. If life was pumping out oxygen for an entire eon, why did the atmosphere remain toxic and anoxic? The early Earth faced a severe thermodynamic problem. 4 billion years ago, the sun was roughly 30% dimmer than it is today. Without an intervention, the entire planet should have frozen solid. The early Earth had an intensely hot interior, which drove a hyperactive system of volcanoes. These constant eruptions saved the planet by pumping enormous volumes of greenhouse gases into the air, creating a thick, insulating blanket. This atmosphere was heavily reliant on methane. Even in small amounts, methane is an incredibly potent greenhouse gas, trapping significantly more heat than carbon dioxide. While this methane-rich greenhouse system kept the oceans liquid, it also created a chemical environment designed to destroy free oxygen on contact. The early Earth was packed with sinks, vast reservoirs of chemicals that hunted and bonded with oxygen, neutralizing it the moment it was produced. The largest of these sinks was the ocean itself. The deep water contained no oxygen, but it was saturated with dissolved iron. As cyanobacteria released oxygen in the shallow waters, it reacted with that dissolved iron to create insoluble iron oxides, essentially rust. This rained down to the seafloor to form banded iron formations, easily identified by these distinct red and gray bands. The atmosphere acted as a second sink. Any oxygen molecule that managed to escape the ocean immediately collided with that thick blanket of methane. The two gases reacted, destroying both the methane and the oxygen. Simultaneously, a geochemical sink operated. Volcanic and hydrothermal vents released constant streams of reactive gases like hydrogen sulfide, which scrubbed whatever stray oxygen remained at the surface. Biology was a leaky faucet trying to fill an industrial drain. Oxygen couldn't accumulate because the entire chemical metabolism of the planet was engineered to consume every drop. Overcoming that bottleneck required a structural change to the Earth itself. Between 2.7 and 2.4 billion years ago, the planet's crust began to mature, establishing deeper, more efficient tectonic recycling. Cyanobacteria making oxygen also create organic carbon. If it decays, it consumes the oxygen back. But maturing tectonic plates dragged this organic waste deep underground. Locked away, it was removed from the equation. The oxygen was left behind, finally overwhelming the chemical drain. The smoking gun for this event is found in the rock record. A specific chemical fingerprint called S. Smith permanently vanishes from global sediments roughly 2.46 billion years ago. S. Smith is only created when harsh, deep ultraviolet radiation strikes sulfur in an oxygen-free atmosphere. Its disappearance proves that atmospheric oxygen finally reached a threshold high enough to form a rudimentary ozone layer, which blocked the radiation. The Great Oxidation Event happened because geology matured enough to store life's waste. But crossing that threshold did not create a sudden paradise. It triggered a near-fatal planetary catastrophe. As oxygen built up, it rapidly oxidized the atmosphere's methane greenhouse blanket, scrubbing it out of the sky. Stripping away that thermal insulation caused global temperatures to crash. Earth plunged into the Huronian glaciation, a planetary ice age lasting hundreds of millions of years. Simultaneously, this new reactive oxygen gas poisoned the existing anaerobic biosphere, causing Earth's first mass extinction. Achieving a breathable world for complex life wasn't a peaceful progression. It was the result of a violent planetary gamble, one where Earth's initial climate system had to crash and burn to make room for the next.